Next, what we want to discuss is the concept of determinant of matrices. Okay, so first let us start with the introduction. So we talked about the determinant for a 2 by 2 matrix. Okay, so we said that if A is equal to A, B, C, D, then we set the determinant of A, which we usually write like this: A, B, C, D is like the absolute value, the bars. Okay, it's just a convention. Okay, so this becomes AD minus BC. And this number appears, for example, when we try to solve linear systems, 2 by 2 linear systems. Okay, and what we saw before is that A is invertible. It has an inverse, invertible, if and only if that determinant is not equal to 0. Remember that if A is not equal to 0, okay, you may not have an inverse. Okay, so we have discussed this issue. It's not like real numbers. A real number has an inverse if and only if is not equal to 0. In this case, what captures the invertibility of a matrix is the determinant. I'm talking about 2 by 2, of course. Okay, and we have even the inverse. We have seen that the inverse, in fact, is given in terms of determinant of A time a certain matrix, which is dA minus B minus C. So we have seen all this before. Okay, so first of all, before we start looking at how can we extend this concept of determinant to matrices which are of size n and bigger than 2, in other words 3, 4, 5, etc., etc., let us see some basic properties of the determinant. Okay, so basic ones. Number one, it's clear that the determinant of A is the same as determinant of A transpose. What does it mean? It means that it doesn't matter whether you are dealing with the rows or you are dealing with the columns. The determinant will be the same. This is the idea. If you deal with the rows, okay, whenever you deal with the rows, you have a similar conclusion for the determinant if you deal with the columns. That's basically what the idea is about. Okay, so 2, what is the determinant of a triangular matrix? Okay, so whether you're taking A, B, 0, and C, okay, that's AC, because minus 0, B will give us 0. This is for the upper triangular. And if you take now lower, it's going to be the same, because we said that the transpose, the matrix transpose has the same determinant. And therefore, what it means is that for triangular matrix, the determinant is just the product of the element of the diagonal. So the determinant is the product of the element or the entries, the diagonal entries. The diagonal entries. Okay. What happened if we change, as we said, whether you do it for the rows or you do it for the columns is exactly the same. So what happened if I start with A, B, C, D, and I interchange 2 rows? So meaning what? The first row becomes the second, and the second becomes So here we're looking at C, D, A, B. So the calculation shows you, in fact, that they are opposite. One will be AD minus BC, and the other one will be what? BC minus AD. Therefore, it's the opposite. Okay, so when you interchange two rows or two columns, the determinant is just simply one minus the other one. What is now, what if we multiply a row by a number? Okay, so if you take, for example, lambda time A, lambda time B, C, and D, so you will find lambda AD minus lambda BC. You factor out lambda, and you will find that this is the same as ABCD. So whenever you have a number, you can multiply. In other words, when you multiply determinant, it's like multiplying a row by that number, only one row or one column. This is totally different from multiplying a matrix. Now remember, we said that if we multiply the matrix ABCD, we multiply all entries, okay, by that number. This is the multiplication of a matrix by a number. For the determinant, no. When you multiply by lambda, a determinant, either you multiply one row or one column. Any row, any column, okay? So what happened if a row has zeros, okay? So if a row has zeros, 5, okay? So if you have a row which is A, B, C, 0, 0, then you will find 0. So if one row is only zeros, then what you have is 0, okay? And you can also get it from number 4, by the way. So by taking lambda equals 0. So if one row or one column is equal to 0, the determinant is 0. And what happens if they are the same? Same. So in other words, here, if you take A, B, A, B, okay? So the same row, or even one is multiple of the other one. Remember, from 4, we can take the constant out, but you will end up having what? 0. If two rows are the same or proportional, the determinant is what? Is 0. 6, these are just basic properties, and it's very, very interesting to go deep into all these properties, okay? So what happened if now what we do is the following, okay? We take A, B, C, and D. And what we do, we take, because of the row elementary operations, we take one row and we add a constant time the other row or another row. So for example, here, what happened if I take A plus lambda C and B plus lambda D and C and D, okay? And it's not very hard to develop it and see, in fact, that is exactly the same. So if you take one row, why? Because you can reduce it to 5 combined with 4. You see, that's the idea here, okay? You can combine it with 5 and 4. One more, 7, which is what happened if you have, say, A, B, C, D, and you want to add numbers to one row, okay? So we add alpha and beta to one row. So here, what is the relationship with, if we add A alpha, B beta, and C D, okay? And what's interesting is that the calculation will tell us that, in fact, that one, okay, B beta, CD is equal A, C, B, D plus, and you take alpha C and beta D. It's just a calculation. In other words, what happened, this is what we know, what we say, that with respect to each row or each column, you are linear. In other words, you are additive. That's the property that you have here. And you have a constant. If you have a constant, it comes out, okay? The next one is not easy, and it needs some work, okay? Which is, what is the determinant of A times B, okay? And this is the determinant of A times the determinant of B. This is amazing, okay? for the product is quite extensive, but it's true. In other words, either you can prove it through different means, okay, or you can prove it just using the formula that we have, okay. So in particular, what happens if A is invertible? So we know that in this case, we have A times A inverse equals I2, okay? And if we use the determinant, we find the determinant of A using the formula we just said, equal determinant of I2, which is 1, because it's going to be 1 minus 0. So the determinant of A is not equal to 0. We knew that because A is invertible. But what's interesting is that the determinant of A inverse, in fact, is equal to 1 over determinant of A. So these are basically the basic properties of the determinant of a matrix, okay? 2 by 2. So the question now, the main question that we'll discuss in the next lecture, the main question, okay, natural question, by the way, which is if A is square of size n by n greater than 3, okay, what is the determinant of A? Okay, and what we want is to preserve these properties that we discussed just before. So from the 2 by 2, okay, and we want to come up with this number, okay, and this problem here, this problem took some time. It wasn't like a simple question and we just have a simple answer. No, it was complicated, very complicated, and it took some time, and finally we have, they started with 3 by 3. Once you get to 3 by 3, then you have the other ones, you know. I mean, we'll discuss this in the next lecture.